So thanks a lot for giving me the opportunity to give this talk. First of all, it's a really exciting seminar series, and I'm glad to be in good company today. So this is going to be mostly a short review talk of what I think of as typical rift volcanism that we find in at least some places in East Africa, definitely not everywhere. I'm obviously also not able to cover everything, so it's not a comprehensive review, but it's a start at least. So first of all, I also wanted to acknowledge some of the people that have helped me along the way in all the years that I've been working in East Africa, which is more than 10 years now. Some of these people have had a supervising role, others a mentoring role. Perhaps they don't always realize it, but I didn't want to miss out on the opportunity to express my appreciation. So this map, first of all, shows the structure of the East African rift and the relation to the volcanoes that we know are still potentially active. So those are all the volcanoes that have been taken up in the Global Volcanism Program's list of Holocene volcanoes. And so often when we think about the East African rift, we think of it as a continental structure that crosses the continents on the eastern side along 3,000 kilometers or so. But obviously it's somewhat much more complicated than that. So we have, sorry, I think do you still see my screen?
Yes, everything's good.
Okay, yeah. I was just looking for my pointer. Yes, there it is. So we have first of all, the eastern branch, which starts off from the Afar Triangle through the main Ethiopian rift, the Kenyan rift, and into the North Tanzanian divergence zone. And together, that's in most places considered to be a relatively mature continental rift. It's clearly magma assisted, lots of volcanoes there, and where a significant proportion of the extensional strain is accommodated aseismically by regular magmatic intrusions. But then next we have the western branch of the rift, where the volcanism is concentrated much more into accommodation zones, which we tend to call volcanic provinces. And so the most important of these are the Virunga volcanic province and the Rungwe volcanic province. So overall, we have about 100 volcanoes that are still believed to be potentially active. About a quarter of these have erupted historically. And so those are the ones that are indicated in red. And all the others, we have evidence for that they might still erupt in the future as well, either because they're actively degassing or actively deforming, or because we have evidence from volcanic deposits that have been dated to be of Holocene age. In addition, you also have some of these areas encircled in red. Those are places where we have abundant andosols. So those are rich, fertile soils that are typically developed onto young volcanic deposits, which provide a good source for cash crop farming. So those are just one example of the plenty of resources that are also associated with the volcanism in East Africa. Lots of resources obviously means lots of people. And so we have altogether about 25 million people living within 30 kilometers of any of the volcanoes in East Africa. So in terms of composition, here is an overview plot. It's your classic total alkali versus silica diagram that we often use for classifying different types of volcanic rocks. These are all data that are retrieved from a publicly available database. And so you see that the compositions in Afar and main Ethiopian rift are fairly similar, spanning from basalt. So those are the blue symbols, spanning from basalt up to rhyolite. And these are per alkaline rhyolite, so relatively rich in sodium and potassium. Further south in the Kenyan rift and also Tanzania in the western branch, we also have basalts on the mafic end, slightly richer in alkalis typically, up to trachytes and phonolite magmas. And just occasionally, for a few specific volcanoes, we have compositions in the phoidite field, which are extremely enriched in alkali elements relative to a relatively low silica content. But those are unusual because they're restricted to volcanoes like Nyiragongo in the Virunga province and Oldonyo Lengai in the north of Tanzania. So in some ways, you might consider them not really typical rift volcanoes as such. You might think that's okay, that's kind of cool. Why is this important? Well, a lot of the models that we use in volcanology and a lot of our observations that we have used to construct models of how volcanoes work and how eruptions work are based on observations at arc volcanoes, and which would have typically compositional ranges also from basalt to rhyolite, but much less rich in alkali elements. So those are your series of basalt going to andesite to dacite to rhyolite. And so, as I said, that's where we base most of our understanding of on crystallization kinetics, thermodynamic properties, and also rheology of magmas. And when we look at the rheology, so these are experimental data of viscosity versus reciprocal temperature on melts of different compositions. When we look at this, we see that alkali-rich compositions have a relatively reduced viscosity compared to calc-alkaline melts. So for example, our peralkaline rhyolites, trachytes, phonolites, they all sit around these viscosities of dacite magmas, and typically 2 orders of magnitude less than or lower than normal rhyolites for a given set of temperature and pressure and volatile contents. And this is of course important because a reduced viscosity will also influence, well, the eruptive behavior of the magma, and should also favor less explosivity during the eruptions. When we look at the volatiles, there's very little data that is available for volatiles in the magmas in continental rift settings. These plots are from a recent paper that came out last year that is looking at the melt inclusions in certain crystals in olivine for basaltic melts and in quartz for rhyolite melts for different volcanoes in the main Ethiopian rift. And here we see that CO2 contents are up to several thousands of ppm in the basalts for water contents of 1 to 1.5%. And so with these combined observations in these melt inclusions of both CO2 and water, we can reconstruct the pressure at which these two contents would have been in equilibrium. And so that gives us some information on the storage conditions of the magmas. Importantly, when we look at the rhyolite compositions, so the melt inclusions in the quartz crystals, we see that the water contents are relatively high. And so they're easily 4, 5, 6, even up to 8% of water. And that is actually very similar to what we see in arc magmas as well, whereas quite a lot of older school textbooks would probably have told you that arc magmas are particularly rich in volatiles. It turns out that rift magmas are maybe equally rich in volatiles as well. And so with all this fairly new petrological geochemical information, we are starting to get a better understanding of the plumbing systems of these volcanoes. So this is a map of the main Ethiopian rift, where we have plenty of caldera volcanoes, silicic calderas that erupt rhyolite melts. And at the same time, we also have a lot of smaller basaltic cone fields, very often fault controlled, either along the rift axis, but also very often off axis. And so with all the combined information from petrology, geochemistry, but also geophysical constraints, we're starting to get better ideas on the plumbing systems. And so this is a schematic plot still from the same paper as I mentioned before. We think that the mafic melts, obviously saturated in water and CO2, would directly feed the off-axis cone fields. For example, the ones that we see here in Butajira or Bishoftu. But then along axis, they could rise to more shallow depths of 5 to 8 kilometers or so, where they fractionate extensively to form highly silicic rhyolites and basically develop reservoirs that are mush dominated. So basically chock full of crystals, but in which discrete pockets of residual rhyolite melt would still exist. And those reservoirs could also develop a volatile rich cap. So it's an exhaust volatile phase that concentrates towards the top. And it's those volatiles that would interact with the hydrothermal system and basically drive a geothermal reservoir that in some places is tapped for resources. And so understanding the chemical composition and also the rheology and the general architecture of the system is of course important to also be able to understand and interpret signals of unrest that I'm sure Juliet will talk about later. So in terms of physical volcanology, we're getting quite a bit of understanding now of how often the volcanoes erupt. We often, well, typically we don't really have anything historically to rely on, so there's very little to no historical observations. And therefore we have to rely completely on the geological evidence. And so that could come from pyroclastic sequences, such as the ones here, that we can measure and log to look at eruption styles and also eruption magnitudes. Sometimes, if we're lucky, we find some finer ash deposits preserved in lake sediments. And those are very good for preserving sort of smaller scale deposits that are not easily preserved on land. And so those lake sediments very often provide additional constraints on eruptive frequency.
10 minutes.
Okay. And so in places where we have these reconstructions, where we've got a fairly good understanding of the eruption history, we tend to find recurrence rates on the order of a few hundreds to a few thousands of years, specifically for, I should mention that, for explosive eruptions of the silicic magma, so the rhyolites and trachytes. So in this equation, I'm not talking about the basaltic melts. And so we know in some places that these magnitudes of these eruptions, these explosive eruptions, could be easily Plinian scale. So they could be developing eruption column heights of 20, 25 kilometers high, even more. And so obviously deposits lots of pumice and ash on a local or even regional scale. However, it's not because you find thick pyroclastic fall deposits, for example, that you're immediately dealing with a Plinian style eruption. And so this is something that is fairly recent development also in modern volcanology in the Rift. It's this concept of pumice cones. So pumice cones are quite typical for alkaline rhyolite volcanoes. And with recent very detailed field work and also textural analysis on the volcanic products, plus combined with high resolution imagery, we're starting to get a better idea of how these volcanoes actually erupt. And so these pumice cone eruptions are fairly unsteady. They tend to develop moderate intensity plumes that can easily collapse to form pyroclastic flows and also gradually build up a cone-shaped landform that at the end tends to be breached by a silicic lava flow or an obsidian lava flow. And so in the proximal deposits, they often preserve these very unusual particles that we call pumiceous agnolites that are very highly inflated on the inside, but which have a smooth skin on the outside. And so it's this kind of information that is, in addition to knowing how often the volcano erupts, that is also very important to understand distribution patterns and really develop eruption scenarios that have now been incorporated into probabilistic scenario modeling, especially for Aluto volcano in Ethiopia. So I'll leave you with these 2 points, just 2 key points to take home. These are, the East African Rift has about 100 volcanoes that are still potentially active, and where we find eruption recurrence rates of a few hundred to a few thousand of years. The rift melts are rich in volatiles and alkali elements, and that has very important implications on the eruption style, and so also on the hazards. Thank you.
Thanks a lot, Karen. We have a few minutes for questions. So far, there are none in the chat. You can also type just Q if you have a question and you don't want to type too much. All right, Katie Whaler has a question.
Yes, Karen, I have asked Juliet this in the past and actually also Mary Edmonds, but it's the question about the whether we know the melt is confined to just beneath the volcanic centers, both off rift and on rift, or whether it could be quite ubiquitous in the middle of the crust. You know, the seismic models show seismically low wave speeds in the mid crust, and when we look at our models of the resistivity, we get relatively conductive material quite extensively, but we don't have very good resolution. So I was wondering if you would say a few words about that.
Well, I think our general idea these days of plumbing systems is that they would be transcrustal anyway. So there might be zones where there is relatively more melt available. Those would be the pressure, the storage conditions that we can reconstruct from the melt inclusions, for example, predominantly a few hundred megapascals, and then zones at about 150 to 200 or so. But there must be pockets of melt and conduits in between. So I wouldn't be surprised if it's a continuous system in any case. Does that answer?
You're talking about continuous in depth, and I'm talking about continuous laterally as well, about whether you would get the melt only focused beneath volcanic centers or whether it could be smeared out laterally.
I don't know if we have much from the volcanology side, if we have many constraints on that. And I don't think, as you mentioned, there's of course a limit to the resolution from the geophysical observations, but the same is true for the petrological observations. The error bars on these reconstructions are significant, I should say. And of course, we only capture certain zone. I don't know if we have much ideas on the lateral extent.
Okay, thanks.
Raphael, you have a question?
Hello, Karen. In such kind of context as the main Ethiopian reef, do you have an idea of the occurrence of silicic volcanism compared to mafic volcanism? My question is, compared to the flux of basic magma that is imputed at the base of the crust, is the occurrence of silicic volcanism some kind of exceptional compared to because of continuous replenishment with basic volcanism, or is it something extremely well constrained, and each batch of mafic melt will give always the same batch of silicic volcanism at the surface?
Well, the only thing we know is that the silicic magmas are thought to have formed from protracted fractional crystallization. So you need 95% or so fractionation. One thing that hasn't been constrained very well is what volumetric budgets would be of silicic versus how much mafic melt you need to be able to fractionate that. And that's something that hasn't been constrained as far as I know. The only thing we do see along the main Ethiopian rift, for example, is that in some places, the silicic magmatism is clearly dominant and is able to develop these shallow crustal systems and then caldera forming eruptions, etc. And we see along the main Ethiopian rift, especially towards the south, that is dominant. That's a dominant style of volcanism, where we also have much less visible cones, for example, at the surface. So we have much less mafic melts that manage to erupt through towards the surface. If you go further north in the main Ethiopian rift, and then of course further north towards Afar as well, then the mafic volcanism seems to become dominant. And so I don't think, again, we have a good understanding of that, but something limits the buildup of these crustal reservoirs in those places.
Oh yeah, I agree completely.